Hey everyone, Nick Diobertis here teaching you financial modeling. Today we're going to be solving the lab exercise on adding Monte Carlo simulation to an existing Python model. So this is part of our lecture series on Monte Carlo simulation. And at the end of the formal Monte Carlo material, we introduced this lab exercise where we're taking the Project 1 Python model and extending it with Monte Carlo simulation. So the situation is that we're concerned that the interest rate is going to be an issue. So we're going to assess changes in the interest rate and how that affects the MPV. So let's jump over to the Project 1 model. So I already defined everything and brought the model function down to here, so we can now work with that. So we're going to need to import the random module to be able to randomly draw the interest rate. And we're going to let's create another data class for simulation inputs. And then we can have the interest mean. What do we say it's going to be? 7% and standard deviation of 2. Interest mean is 7. Interest STD is going to be 2% by default. These are both floats. Okay, and then we can do sim data equals simulation inputs and bring back our data equals model data. Okay, so we can draw these interest rates from a normal distribution, the sim data interest mean, and the sim data interest STD, and that will get us random interest rates as we see. So then we can work this into a new setup where we're going to draw the interest this way. And then we're going to create the data by passing this interest rate. So interest is going to equal that interest that we just calculated. And now we see that we have the model inputs, but with the new random interest rate included in there. And so now we can pass that new data to the model, and we see that we get a new MPV. So that's one simulation for us. So let's go ahead and create a function for that. So I'm just going to call the function simulation. It's going to take the data and the sim data. Actually, it doesn't need to take the data, it's just using the sim data. And it's going to do this, everything that we just looked at. So now we have a simulation function that we can pass our simulation data and see a different MPV each time. So everything seems to be working correctly. And we can make it return not just the MPV, but also the interest as well. So now we see the interest rate that produced that MPV. So if I put this into a list comprehension, and let me go back and add a number of iterations. into this. So let's just keep it at 10 to start out with. We'll increase it later. So simulation, for I in range, sim data dot and iterations. And then we'll see that we have that many results now with different random interest rates and different random MPVs. So then let me import pandas. And so now I can create a data frame from those results. And the columns are interest and MPV. So now we have a data frame of the results. So let's create a function for that. Simulations data frame. Again, takes the simulation data, does this, and then returns the data frame at the end. So now we can do simulations df on whatever simulation inputs we want. If we want to put 100 iterations, then we can see we get 100 here. And I did, let me just go and change the default to 10,000 now. So we can just put this back to sim data. And we have 10,000 simulations. Okay. And now we can look at the resulting probability distribution of the MPV. So if we look at MPV, and I don't need any of these anymore, and we want to look at a histogram with 100 bins, let's see how that looks. So looks roughly normal. Maybe the tail is a little bit longer on the right-hand side, but mostly normal. And centered around this, what's that? 30 million, or 300 million, right? Yeah. So centered around 300 million. Sometimes going past, most of the time between 250 million and 400 million. Sometimes going higher than that, sometimes going lower, but not very often. So then we can also look at the percentiles of the distribution. Before I do that, I'm going to create a styler function for the data frame because we'll use that over there as well. So I'm just first looking at the first few rows of the data frame, so this thing isn't going to be huge with 10,000 rows. And then I'm going to format the numbers here. So interest, I'm going to use 2 decimal place percentage formatting, and MPV is going to be dollars, and with commas and 0 decimal places. So then this should look a little bit better. Yeah, now it's very clear that these are 300 million, etc. And so now I'll convert that into a styler function. And then I don't need the head anymore. And I can just call this on df.head. And it is indeed working. So we'll come down here. Now we can get our percentiles that we want to look at. So I'm going to look at 5% increments. So you can see there, 5% increments. And then I'm going to call quantile on that. And here you see it has that same not great formatting. So I'm going to call styled df on that. And now we can see it has the nice formatting. And so this quantifies the same thing that we're seeing in this histogram. Most of the time, we're in the 300 million kind of range. 5% of the time, it will get as low as 250 million. 5% of the time, it will get over 400 million. And then the question, so table of probabilities, visualize the results. Then we also want to output the chance that the MPV will be more than $400,000. So we can check this. So DF MPV greater than or $400 million, $400 million. So that gives us a series of true or false for whether it was greater than $400 million. We can take that and convert it to integers, 0 or 1, for whether it's greater than $400 million, and then take the average, and that's going to tell us how often this is going to occur. So let's save that in a variable so that we can then print out a string which gives meaning to that. So there is a percent with the percent formatting, chance that MPV will be greater than, might as well make this a variable as well. Cutoff is going to be this 400 million, greater than cutoff. There, let's put a $, commas, and 0 decimal places. Okay, so now we have a nicely formatted result here. There's a 6.37% chance that the MPV will be greater than 400 million. So that's the level 1 exercise. Now coming to the level 2. So now we're also concerned about the number of phones per machine. There could be some issues in the assembly line. And so we're going to add that in. And then beyond what we were already doing with visualizing the results, we now also want to look at the relationship between the inputs and outputs, visualize those relationships, and run a regression to quantify those results as well. So we can come back up here, and we're going to need a couple more simulation inputs now. So now, what is the original input called? Just to keep it consistent. End phones. So end phones mean was 100,000. End phones standard deviation is going to be 20,000. So then, in addition to drawing the interest, we can do the same with the number of phones. So I'm going to switch these out for n phones, and then also pass n phones equals n phones here, and then also return that in the result. Then add that into the data frame, and add that into the styler as well. We're just going to have commas and 0 decimal places. Okay. And then, okay, yeah, I've got to actually run this. Let me put this before that. And now we see interest rate, number of phones, also random, and both of those factoring into the MPV. So then we can re-examine these things, the MPV. Now, pretty similar, going over a slightly larger range than before. Quantiles, same thing, slightly larger range going on here. And now there's a little bit better chance that we're going to be able to get the 400 million. But now what we're doing additionally is to analyze the relationship between the inputs and outputs. So one way we can go about that is scatter plots. So set x equal to interest and y equal to the NPV. And we can see a scatter plot between the two. And let's make this for interest and for number of phones. We're going to do this same scatter plot. So we can see with the interest rate that it looks like there's a very, very clear relation here. Seems to be almost linear, kind of a curved relationship, but definitely a clear pattern there. Those two look very strongly related. As for the number of phones, it's not so clear. These mostly look like an ambiguous cloud, but it does seem to be going a little bit up and to the right. So it's not very clear. It certainly looks like it's not as strong of a relationship as interest in NPV. And it's a little bit ambiguous about whether there's a relationship. We really have to quantify this to understand that better. So the next step is then to run the regression. I'm going to come back and add the import for stats models. And then I'm going to set up the X is going to be the data frame, the interest column. Whoops, I put an extra brackets. Wait, no, that was correct. Interest column and number of phones. Yep, got them both. Y is going to be the MPV. And we're going to want to add the constant to the X. And then we can create the model as sm.ols of y and then x has constant equals true. Result, we're going to fit the model to get the result, and then we're going to summarize the result. It did not converge. Okay, that's interesting. Everything looks correct there. Everything looks fine here. Yeah, the order is correct. It worked fine that time. I'm not quite sure what happened there, honestly. But I'm happy it worked this time. So looking at the results, first thing we'll notice the p-values are all 0, which means these are all significantly related to each other. And then we can interpret the coefficients to understand the relationship. So here, when we get one additional phone made by each machine, then we're going to get $768 additional of MPV, holding the interest constant. And then this is quite a large negative number. And that's because the interest is in decimal. And so that's saying going from 0 to 100% interest, which doesn't make a lot of sense to compare. Really, we want 1/100th of that coefficient. So when we look at it divided by 100, and that would be that the MPV drops by 23 million when the interest rate increases by 1%, which makes sense. But this still doesn't tell us which one has a larger impact because we have to look at the standard deviation in order to assess that. Um, the standard deviation of the data frame. And we can multiply that by the parameters, the coefficients, and this will give us the standardized coefficients. Now saying a 1 standard deviation increase in the number of phones will increase NPV by 15 million, and a 1 standard deviation increase in interest will decrease the NPV by 46 million. So it looks like the interest rate has approximately a 3 times greater impact in the model than the number of phones, assuming that we've picked reasonable distributions for the inputs. So that is everything involved in this lab exercise. So thanks for listening and see you next time.